lecture 26 of our series on numerical methods in civil engineering, we will wind up our discussion of analytical solutions for partial differential equations by talking about series solutions for elliptic to partial differential equations, and then move on to numerical methods for solving them. We will talk about differential operators. Before moving on to before actually talking about series solutions, I want to recapitulate a little bit. I just want to talk briefly about something we discussed last time, that is the method of Green's functions for solving partial differential equations. Why do I want to do that? Because this method is crucial to our development of series solutions. We saw that it is possible to construct Laplace's equation, solutions to Laplace's equation using Green functions. And what are these Green functions? These Green functions, they satisfy Laplace's equation and they satisfy the boundary conditions homogeneously, right? And to construct Green's functions, we used Green's identities. We talked about the first, second and the third identity of Green. We defined smooth functions phi and psi defined over a volume V with boundary del V, in which case we get the first identity psi Laplacian of phi is equal to psi del phi del n over del V and minus grad psi dotted with grad phi over V. So, that was our first identity. Then this was our second identity, which we got basically from the first identity by interchanging phi and psi and then subtracting that from this first identity. And this was our second identity, which was psi Laplacian of phi minus phi Laplacian of psi is equal to psi del phi del n minus phi del psi del n. And then we looked at Green's third identity. In order to get Green's third identity, we assume that the function phi is harmonic, that is Laplacian of phi is equal to 0. In addition, we assume that psi is the fundamental solution to Laplace's equation, right? And we recall that that fundamental solution is given by psi is equal to 1 by 4 pi r in spherical coordinates, where r is the position from the reference from the origin, right? R is the distance from the origin, not the position actually here. R is the distance from the origin, right? And we saw that this solution, this phi 1 by 4 pi r, satisfies Laplace's equation everywhere in the domain except at the origin, where it becomes undefined, right? It becomes, and actually becomes, and that led to our discussion of the Dirac delta function, right? That led to the Dirac delta function. So, we substituted that in Green's second identity and used the fact that Laplacian of minus 1 by 4 pi r is actually equal to the Dirac delta function delta x minus y operating on phi y equal to phi x, whence we got phi x is equal to this, right. So, then we said that this tells me that if I know the value, if phi satisfies Laplace's equation and I know both the value of the function as well as its gradient at the boundary, then I can use this equation to find out my solution to Laplace's equation, right. So, using these boundary conditions, see the integral is over del V, which is the boundary. So, provided I know this and I know that at the boundary, I can solve for phi x. Then I went on to say that it is almost never possible to know both these values at the boundary, because otherwise the problem becomes ill posed, right. And the solution to that was to look at Green's functions, right. Solution was to that was to look at Green's functions and say that psi is not actually equal to 1 by 4 pi r, but it is equal to 1 by 4 pi r plus another function u, where u is also harmonic, right. Laplacian of u is equal to 0 in domain V, in which case we get the following. We got the following: phi x is equal to g del phi del n minus phi del d del n minus g Laplacian of phi dy, right. And if phi satisfies Laplace's equation, this part becomes 0 by definition, right. This part becomes 0 by definition, and we have phi of x is equal to g del phi del n minus phi del g del n, right. And now, if we construct the Green's function to be g is, if we construct it in such a way that g is equal to 0 everywhere in the boundary, right, g is equal to 0 everywhere in the boundary, then we get phi x is equal to minus integral del v phi del g del n ds y, right. So, the only requirement, that only thing that we need to know is that we must know phi all over the boundary, right. Del g del n is known, right. Green's g is a known function, g is a known function. So, del g del n is known. If we can find out how phi is distributed on the boundary, right, then we can always find phi. So, this gives us a way for finding phi when we have Dirichlet boundary conditions. On the other hand, if g satisfies the condition del g del n equal to 0 and del v, then solutions can be found using this expression, right. Phi x is equal to g del phi del n. So, in this case we have to know del phi del n on the boundary, that is, we need Neumann boundary conditions on phi to be prescribed on the boundary. I think that is where we stopped last time, right. We talked about Green's function and that is where we stopped. Next, we want to consider series solutions of Laplace's equation. The example we will consider will involve a body with finite boundaries lying in an infinite domain. So, you can think of a body, a solid lying within an infinite fluid. For instance, a spherical inclusion, right, a spherical inclusion, a spherical solid moving with a certain velocity u in an infinite fluid medium, which is otherwise motionless. Think of simple example would be a submarine, right, a submarine flowing through the ocean. The ocean is still, right, the submarine moving through, or any just the simplest example is a sphere moving through a very large water body, right, a water tank suppose, where the boundaries are so far away that we can assume that the water tank is infinite, right. And what we are interested in knowing is that, okay, the sphere is moving with a velocity of u, but what is the effect of that motion of the sphere on the fluid, right? What is the effect of the motion of the sphere on the fluid? So, we are interested in finding the disturbance in the fluid, that is its velocity, that results from the motion of the sphere, right. And if the fluid is irrotational as well as isochoric, irrotational meaning curl of the velocity is equal to 0, and isochoric means divergence of the velocity is equal to 0, then there is a potential, right, the potential, and by taking the gradient of the potential we can find the fluid velocity, and the potential satisfies Laplace's equation. So, the potential is harmonic. So, again in this case we are back to finding the solution of Laplace's equation, right, because once we find phi we can find the velocity, right. The v is the gradient, the velocity of the fluid is the gradient of phi. So, hence we need to find solutions to Laplace's equation, Laplacian of phi in an infinite domain. So, this is my infinite domain, right. Here is my little solid body, right, and here is my origin of my spherical coordinate system, and y is the vector from the origin to any point on the surface of my solid body, and x is a point far out in the infinite domain, right, where I want to find my solution, right, where I want to find my velocities, right. So, the vector y represents the position of a point on the boundary of the submerged solid with respect to the origin, while x is a position vector to a point in the infinite domain lying sufficiently far outside the body. So, this mod of y by mod of x is less than 1, right, that is a requirement, right, and mod of x is of course equal to the length of this vector and mod of y is the length of that vector. So, under the condition mod of y by mod of x is less than 1, we can expand. Recall our fundamental solution is given in terms of 1 by r, right, 1 by r, right. So, if I can expand 1 by mod of x minus y, 1 by mod of x minus y using a Taylor series, right, and if this condition is satisfied, the Taylor series is uniformly convergent, right. So, mod of 1 by mod of x minus y, that is I am expanding about x, right, I am expanding about x, and my displacement from x is given by y, right. So, I am expanding about x. So, 1 by mod of x minus y is equal to the value of the function when y is equal to 0 plus the value of the derivatives at y equal to 0 times the perturbation times the change in y, right. So, partial of this with respect to x1, partial of 1 by mod of x minus y with respect to x1 times the change in the first coordinate of y, first, right, minus y1, right. Similarly, partial with respect to x2, change in the second coordinate of y, that is y2, partial with respect to x3, change in the third coordinate of y, y3, right. So, that is the first term in my Taylor series. Then I have the subsequent terms which involve the second derivatives, right, del x1 square, del x2 square, del x3 square, and then the mixed derivatives del x1 del x2, del x1 del x3, del x2 del x3, and so on and so forth, right. And then so this actually becomes, if I denote 1 by mod x by r, right, 1 by mod x by r. So, this becomes 1 by r plus minus 1 by x1 del x1 1 by r. You can see why that would be 1 by r, because y is equal to 0, right. So, 1 by mod of x minus y becomes 1 by mod x, which is equal to 1 by r, right. So, that we get something like this, 1 by r minus y1 del x1 1 by r plus minus y2 del x2 1 by r minus y3 this thing, and then the second derivative. Second derivatives, you can see I can write it in a convenient fashion by taking the product of this, the coefficient of the operator as it acted on the first, in the first derivative, right, which was minus y1 del x1 operating on 1 by r, minus y2 del x2 operating on 1 by r, minus y3 del x3 1 by r, right. So, it is as if I pull out 1 by r and I am looking at the operator minus y1 del x1 minus y2 del x2 minus y3 del x3 operating on 1 by r. And you can see that these second derivatives are actually represented by this operator operating on this operator, and then the result operating on 1 by r, right. It can be written like that, right. So, if I represent this operator as y dotted with grad x, you can see this is y dotted with grad x, right, because it is y1, actually it is minus y dotted with grad x, because it is minus y1 del x1 minus y2. So, grad x is del x1 I plus del x2 j plus del x3 k. So, this is y dotted with grad x with a negative sign, right. So, this equation can be written compactly as 1 by r minus y dotted with grad x 1 by r minus y dotted with grad x operating 2 times, right. So, y dotted with grad x operating on y dotted with grad x, we are writing that as y dotted with grad x square by factorial 2 operating on 1 by r plus higher order terms. So, I can write it in index notation as a summation as minus y dotted with grad x to the power k divided by factorial k operating on 1 by r. So, that is my Taylor series expansion of 1 by mod of x minus y, right. Now, let us go back to Green's third identity, and remember that Green's third identity gave us the solution for phi when Laplacian of phi was equal to 0 and when psi was 1 by 4 pi mod of x minus y, right. So, phi of x in that case we found was this we have already seen, right, for Green's third identity, from Green's third identity. Now, what we are going to do, we are going to replace that series expansion for 1 by mod of x minus y in Green's third identity, right, Green's third identity, and then we are going to integrate with respect to y, right. So, substituting the above expression for 1 by mod of x minus y in Green's third identity, we get the following: phi x is equal to sigma k equal to 0 to infinity 1 by 4 pi integral over the boundary minus y grad, I dropped the x because that is sort of understood, right, to the power k operating on factorial k 1 by r, right. I could have put an x here. So, this x is actually, this is not really x, it is the gradient with respect to x, right. So, this is gradient with subscript x, right. Is that clear? I hope I should have probably been more careful with it, but I meant that, right. So, gradient subscript x, and then finally, I have dropped the x, right. I have dropped the x and denoted that just by the gradient, right. So, y dotted with, so I get this sort of an expression, and then I integrate, this is a function of y, right, that is a function of y. So, I integrate this, I perform the integration over y, right. If we perform the integration with respect to the variable y over the boundary del v, we are left with an expression involving partial derivatives of 1 by r with respect to x, right. This grad is with respect to x, right. So, partial derivative of 1 by r with respect to x1, x2, x3 for various orders, right. Is that clear? I think that should be fine, right. So, the final expression for phi would be of this form. So, after we integrate out the y dependence, so integrate out all the terms which depend on y in this expression, right, we get an expression for phi like this. So, we get a first term which is 1 by r plus this derivative terms del x1, del x2, del x3, and these coefficient terms. The coefficient terms involve the integral with respect to y, right. Whatever I get after integrating with respect to y, those are my coefficient terms. So, those coefficient terms appear here, and I have 1 by r here. Similarly, I have these coefficient terms here, and I have operating on 1 by r. So, writing this in concise notation, we have a0 grad x 0 1 by r plus a1 grad x 1 by r plus a2 grad x square 1 by r, and so on and so forth, where this is my a1, this is an a1 vector, right, a1 vector whose components are a1 1, a2 1, a3 1, right. A2 is no longer a vector, it is a tensor, right, and its components are a1 1 2, a1 2 2, a1 3 2, right, a2 1 2, a2 2 2, a2 3 2. So, this becomes a tensor, this is a vector, that is a scalar, right, and all of them are all of them act on these gradients of various orders of 1 by r, right. So, this I can together I can sum it up as sigma n is equal to 1 to the power infinity a n grad x to the grad x n 1 by r. So, that is my final series solution. That is my final series solution, and this series solution is in terms of what are known as spherical harmonics, right. They are known as spherical harmonics. As I said, a0 is a scalar, a1 is a vector with components like this, a2 has components like this. But let us go back to this term. So, each of these coefficients, whether they be scalars, vectors or tensors, they are operating on this grad x with raised to some power operating on 1 by r. Now, each of these terms we saw last time, each of these terms, whether it be grad x 1 by r or grad x square 1 by r or grad x 3 1 by r, each of them are solutions of Laplace's equation. We saw that last time, right, because Laplacian of x has got constant coefficients. So, Laplacian of grad of something is also going to satisfy Laplace's equation, and since grad of something satisfies Laplace's equation, second gradient is also going to satisfy. So, each of these terms each of these terms grad x n 1 by r, they are solutions of Laplace's equation, and these are known as spherical harmonics of various order, right, x to the power 0, x to the power grad x 1 by r, grad x square 1 by r, grad x cube 1 by r, these are known as spherical harmonics. So, we can think of that as these are the basis for my solution for Laplace's equation, right. Phi in terms of some coefficient, sum of some coefficient times some basis, right, and these bases, these are these spherical harmonics are like my basis for the solution of Laplace's equation, right. Like when we looked at the eigenfunction approach, we looked at the eigenfunctions were the basis. So, these in my series solution, these spherical harmonics are my basis for the solution of Laplace's equation. So, as seen earlier, each term in this series is a solution of Laplace's equation, and this sum is known as the multipole expansion, right. This sum is known as the multipole expansion, and nth term in the sum a n grad x raised to the power n 1 by r is called a multipole solution of order n, right. A n is known as the nth order multipole moment. In particular, a 1 grad x 1 by r when n is equal to 1 is known as the dipole solution with moment a 1, right. So, we got a solution for spherical harmonics, a solution for Laplace's equation, series solution in terms of spherical harmonics, right, in terms of spherical harmonics. And we saw that each of those spherical harmonics is actually a solution of Laplace's equation by itself, right. So, each of the scalar components, this is of course I have said before, but just to reiterate, each of the scalar components of the dipole moment a n are obtained by integrating the y dependent terms of the integral, right, of that integral, of this integral, integrating the y dependent terms, we get those coefficients, right. So, get those coefficients over the boundary del v of this solid body. For example, L a 0 can be obtained like this, and the set of solution of Laplace's equation given by that are known as spherical harmonics, right. So, that is one approach to the series solution of Laplace's equation. An alternative approach uses the method of separation of variables, right. It uses the method of separation of variables, with which I am sure all of you are familiar, right. So, it assumes that the solution of Laplace's equation in spherical coordinates, it is going to depend on all three spherical coordinates, right. It is going to depend on r, it is going to depend on phi, and it is going to depend, I have replaced phi with phi tilde just to distinguish from the solution which is also phi, right. So, it is going to depend on r, it is going to depend on phi tilde, it is going to depend on theta, right. And if I am assuming that if the solution can be written out in separable form, right. So, the functional dependence on r can be written separately from the functional dependence on phi tilde, and as well as the functional dependence on theta, right. So, it can be written out in separable form, and then we are going to solve the same problem, which is the same problem, meaning the motion of a sphere in an infinite fluid, right. So, if we do that, again we have to solve Laplace's equation, right. Again we have to solve Laplace's equation, and then I am going to make a little assumption here. I am going to assume that the solution does not have theta dependence. So, I am going to assume, you can solve the most general way, right, assuming that the solution depends on r, phi tilde as well as theta, but for the time being I am going to I am going to solve the problem assuming that there is no theta dependence. So, the solution phi depends only on the radial distance r and on phi tilde, and we will see that in that case we have, in order to obtain the solution, we have to solve the Legendre differential equation, right. This gives rise to Legendre equation and yields a series expansion in terms of that involve Legendre polynomials, right. Now we are going to get a series expansion in terms of Legendre polynomials. So, this part you just ignore, right, in terms of Legendre polynomials, right. So, we will consider a solution of this nature, but we will do so under the simplifying assumption that the solution has no theta dependence, right. That is phi tilde is equal to, now I have messed things up quite badly, the notation, because my solution now is actually I am calling phi tilde, right, and the angular dependence is phi and the radial dependence is r, right. So, I want to find, so Laplacian of phi tilde is equal to 0, right. Sorry for the confusion in the notation, right. So, then Laplace's equation in spherical coordinates is given by that which we have seen before, only difference is that now I have removed the theta dependence, right. I have removed the theta dependence, I only have the dependence on phi, and then I substitute phi tilde is equal to g of r h of phi, right. If I substitute that there and I divide both sides by gh, I get this equation, and you can see this becomes an ordinary differential equation, right, because this involves only derivative with this r has no phi dependence, while on this side there is no r dependence, right. So, this becomes an ordinary differential equations, and in this case both sides must be constant, because if we change r we will change the left hand side while the right hand side would not change, that is impossible, right. So, what does that mean? That means both sides must be constant, right, both sides must be constant. So, basically now we have to solve these two differential equations, right, these two differential equations, equate them to a certain constant, right, and solve them, right. So, we didn't, let us suppose that 1 by g d dr r square dg dr is equal to n plus 1 and 1 minus 1 by h sin phi d d phi sin phi dh d phi, which is basically these two equations, right, both of them are equal to n times n plus 1. Why did I use n into n plus 1? Because that is the standard form of Legendre equation, you will see just very soon, right. So, we get two equations, 1 by sin phi d d phi sin phi dh d phi plus h n plus 1 is equal to 0, one equation, and the other equation is 1 by g d dr r square dg dr is equal to n plus 1, right. So, we solve the second equation first. The second equation has a very nice form, you can see why, because you can see the first term involves r square and it has a derivative with respect to g, second derivative with respect to g. The second term involves r and it has involves first derivative with respect to g, while the third term does not involve any r, it just has g, right. So, the solution, this is known as an Euler-Cauchy differential equation, right, it is a standard form, and the solution to this equation can be found, this is in terms of r to some power a, right. The solution, if the differential equation is of this form, right, it is a standard form, and what is that standard form? That standard form is known as the Euler-Cauchy equation, right, and for the Euler-Cauchy equation the solution is given by r raised to some power, right. You can see if you raise, if that is obviously going to satisfy that equation, right. R a, if I take the second derivative of that, that is going to give me r a to the r a minus 2, right, r a minus 2 r square, that is going to give me r a. So, it will be some coefficient times r a, second term again is going to give me r a minus 1 times r, so that is going to be r a times some coefficient in terms of a, the third term is just going to be r a. So, every term is going to have r a, I pull out r a, right, and then I have an algebraic equation in terms of the coefficient a, right. In this case, since it's a second order, it is a quadratic, right, it is a quadratic equation in a, I solve that quadratic equation, I get the roots of a in terms of n, and in this case the roots come out to be n and minus n minus 1, right. So, what does that tell me? That tells me that in this case the solution G, there are two solutions. One G involves r to the power n, the other solution involves r to the power n plus 1. R to the power a is the solution. So, a was n and minus n minus 1. So, my G is, there are two parts, G has there are two solutions, right. One solution is Gn equal to r to the power n, and the other part which I denote by G star, which is equal to 1 by r n plus 1, right. So, we have solved the second equation, right, and we have solved that equation and found that the solution involves powers of n, right, powers of n, positive as well as negative powers of n. And now we want to solve this second equation. You can see there are terms like sin phi, d phi. So, obviously, this is a candidate for transformation of variables, right. This is a candidate for transformation of variables. So, what is the transformation we do? Well, we said cos phi is equal to w, right. Then sin square phi is equal to 1 minus w square, right, and d d phi can be written as d dw dw d phi, which is equal to dw d phi. So, minus sin phi d dw, because cos phi is equal to w. So, dw d phi is equal to minus sin phi. So, minus sin phi d dw. So, in that, then if I substitute that in this equation, I finally get an equation like this in terms of whether independent variable, where the derivative is with respect to w, right. So, d dw 1 minus y square dh dw plus n times n plus 1 h is equal to 0, which is the famous Legendre equation, right. And for integers n is equal to 0, 1, 2, this Legendre equation has solution in terms of the Legendre polynomials, right. P n w, P n w is again cos phi. So, P n cos phi are the solution of these equations. So, if you remember these Legendre polynomials, they also are orthogonal to each other, right, and they form a basis, right, and they form, so they are orthogonal to each other. So, combining, there are a lot, the Legendre polynomials are probably one of the most useful, right, expansions, right, expansion in terms of Legendre polynomials, and they are very interesting properties, but at this point we do not want to go into that, right. I just want to tell you that eventually we are going to solve Legendre equation. Solution of Legendre equation is in terms of Legendre polynomials, and using those Legendre polynomials we are going to construct our solution of Laplace's equation, construct our series solution for Laplace's equation like we did with using spherical harmonics. But now we are instead of using spherical harmonics as our basis for our series solution, we are using the Legendre polynomials. We are going to construct that series solution with the Legendre polynomials as our basis. So, combining these expressions for G and H, we get two series solutions for Legendre equation. The first series solution involves the positive powers of R. We saw that Gn has got two solutions, right. The first solution involves the positive powers of R, Legendre polynomials. The second solution involves the negative powers of R, Legendre polynomials, and An and Bn are constant. You can, just by looking at this equation, you can see that this gives the solution in two entirely different domains, right, two entirely different domains. Why? Because this gives me the solution outside my rigid body, right, outside my sphere, right. As r goes to infinity, this is going to go to 0, right. This cannot be the solution inside the sphere, because when r goes to 0, this is going to blow up, right. So, this is going to give me the solution outside the sphere, that is going to give me the solution An Rn Pn cos phi. This part is going to give me the solution inside the sphere, right. Even when r goes to 0, this part remains well behaved, right. So, that is going to give me the solution inside the sphere, inside my rigid sphere or my inclusion, whatever it be, right. and this part, this Bn 1 by Rn plus 1 Pn cos phi is going to give me the solution outside the sphere, right, because this solution is well behaved when we go to infinity. When r goes to infinity, this part of the solution is well behaved. When r goes to 0, this part of the solution is well behaved, right. So, this gives the solution basically two different parts of the domain, right. The solution of the interior problem, that is, if we are interested in velocity or temperature, whatever, if we are solving a different problem, we are interested in the temperature in the interior of the sphere, are obtained from 1, from the solution 1. The solution of the exterior problem, the problem which motivated our series solution, because we are interested in the velocity in the fluid, right, due to the motion of that body in that infinite domain, is obtained from the second part, second solution, right. So, both these series solutions of Laplace's equation involving spherical harmonics as well as Legendre polynomials are widely used in fluid mechanics, bubble dynamics, and study of acoustic phenomena. There may be many other applications, but I am familiar with these applications. I have seen this being used there, so I am talking about these, right. But I am sure there are many other applications of these series solution of Legendre equations. Is that clear? Okay. So, that brings us to an end of our discussion of analytical methods for partial differential equations. Just to recap, we looked at the three canonical forms, right, of second order partial differential equations with constant coefficients, and then we looked at the solution elliptic, we looked at hyperbolic solutions, right. We looked at the D'Alembert solution, we looked at the solution in terms of eigenfunctions, right, the eigenfunction solutions. Then we looked at the parabolic solution, the parabolic equation, the solution for the parabolic equation in terms of again eigenfunctions, and we also looked at the solution for the parabolic equation using transforms, using Laplace's transform, right. And finally, we looked at elliptic equations, right, Laplace's equation, we looked at the fundamental solution, right. We looked at how we can solve that equation using Green's function, which is a very powerful technique because it can be used for very different boundary conditions, various boundary conditions, right. And then finally, we looked at series solutions for Laplace's equation using series either in terms of both in terms of spherical harmonics as well as Legendre polynomials, right. So, these are some powerful analytical techniques for solving second order partial differential equations, linear partial differential equations, right, very important to remember that. So, we have looked at how physical phenomena is modeled using partial differential equations, and we have also looked at analytical techniques for solving them. However, analytical techniques are possible for relatively limited class of problems. For instance, we have seen mostly linear problems, and numerical techniques have to be used in other cases. The first step in the numerical operation numerical solution is to represent all those differential operators which we saw in our equations, del x square, del t, all those things. We have to represent them in terms of difference operators, right. These we have to represent them in terms of appropriate numerical representations, right, and inevitably those representations lead to errors, right, both truncation errors as well as round off errors. So, we have to look at how we represent these operators, right, and most importantly we have to understand what is the error that gives rise to any particular representation, right. So, accurate numerical analysis of partial differential equations require awareness of the magnitude of the error we are introducing because of numerical representation of the differential operators, right. This requires knowledge of the leading term in the error expression. We want to know the leading term. So, we know the order of the error, right, due to either discretization in the space or the time domain. So, we will consider the use of certain operators that are invaluable in the study of numerical methods for partial differential equations, and these two operators I am going to talk about first. First is the shift operator, and then I am going to talk about the difference operator. What is the shift operator? Well, if I have a sequence, right, y0, y1, y2, ym, the shift operator basically shifts that sequence. So, it shifts each term to one term on the right. So, y0 becomes y1, y1 becomes y2, yn becomes yn plus 1. The shifting operation E operates on each term of the sequence and advances each term by 1 to the right to create a new sequence, right. Thus, Ey is equal to y1, y2. So, y0, y1, y2, y3, yn now becomes, after I have operated with that on E, it becomes y1, y2, y3 through yn plus 1, right. The differential operator delta, on the other hand, creates a new sequence by subtracting each term in the sequence from the term to its immediate right. So, my original sequence was y0, y1, y2, y3 through ym. So, after I operate on that sequence with the differential operator, my first term in the new sequence will be my second term in my original sequence minus the first term in my original sequence. My second term in the new sequence will be my third term in my original sequence minus my second term in the original sequence, and so on and so on and so forth. So, my first term in my new sequence is y1 minus y0, my second term is y2 minus y1, my third term is y3 minus y2, and so on and so forth. So, this is the difference operator operating on the sequence y. So, repeated application of both shift operator and difference operator lead to additional sequences. You can see, right, as you operate again and again, I am going to get additional sequence. For instance, for the difference operator, if I, instead of taking different, let me call that as delta y, I am going to refer to the difference operator as delta. So, instead of delta y, if I have delta square y, that is going to not delta y of the first term of that sequence involved y1 minus y0, right. If for delta square y, it is going to involve additional terms in the sequence, right. For instance, eky, so if now we are talking about the shift operator, eky basically shifts each term in the sequence k places, right. So, y0 becomes yk, y1 becomes yk plus 1, and so on and so forth, while delta ky, known as the kth difference of the sequence y, is a sequence where each term in the sequence involves k plus 1 terms in the original sequence. This leads to rapid growth in the number of terms. For example, del square y, you can see that is equal to del operating typical term. If I consider a typical term in my sequence to be yn, right, it is del square y, that is equal to del operating on del y, right. Del y in a typical term yn is yn plus 1 minus yn, right. So, del yn plus 1 minus ym is equal to, again this term has got to be shifted and subtracted from itself, right. So, yn plus 2 minus yn plus 1 minus del operating on this term, that is going to shift that term to yn plus 1, and I am going to subtract yn from that term, right. If I combine those two together, I have yn plus 2 minus 2 yn plus 1 plus yn, right. So, this operating on that gives me yn plus 2 minus yn plus 1. This operating on yn gives me yn plus 1 minus yn. So, eventually I get this. So, this is the, if I apply the difference 2 times, if I apply the difference k times, you can see that there will be many more terms in my difference expression. Now, it is important to remember that both the E and the delta operator operates on sequences, right. Thus, while it is allowable shorthand to write del square y0 is equal to y2 minus 2 y1 plus y0 as we just saw, right, we must remember that this is just the first term of the sequence del square operating on y, right. So, it is the first term in that sequence, right. The first term on that sequence meaning the term that results from del square operating on the first term in my original sequence, right. Now, it can be shown that k operations of the difference operator delta on a sequence leads to a new sequence, right. Then plus 1th term of which is represented by the action of delta k times on the n plus 1th term in the original sequence yn. Suppose in my original sequence by n plus 1th term was yn, right, because I started from 0. So, my n plus 1th term was yn, right, and if I operate on that yn term with n times with my difference operator, right, then I am going to get this thing. If I operate on this yn n plus 1th term in my sequence, in my original sequence, k times, right, I take the difference k times, then I will get something like this, where c is the combinatorial expression, right. So, k c1 is factorial k divided by factorial 1 times factorial k minus 1, right. So, this is my operation, right. So, this can be, this is going to be this. Well, I am going to show it, but I am going to show that by induction. So, how am I going to do that? Well, for k equal to 1, this expression is going to give me del 1 yn, right. That is going to give me del 1 yn. So, I have just denoted by del ym, and that this expression is going to give me yn plus 1 minus 1 c1 yn plus 1 minus 1, that is yn plus 1 c2 plus yn plus n minus 1, and so on and so forth. But you know that when this is 1 and that is 2, when this is greater than that, all these things become 0, right. So, all these things become 0. So, only the first term is going to survive, the first term and the second term are going to survive. So, in that case, what are we going to get? We are going to get yn plus 1 minus 1 c1 yn plus 1 c2 yn minus 1 plus 1 c3, so on and so forth. And since k c k prime is equal to 0, if k prime is greater than k, so this is going to give me del operating on yn is equal to yn plus 1 minus yn, which agrees with the definition. So, we know that this definition that we just gave holds for k equal to 1, right. Now, let us assume that it holds also for k equal to p, right. So, it is the same thing. If p is equal to 1, then we can show that it is, since it holds for k is equal to 1, we can show that it holds for k equal to 2, right. And suppose suppose it holds for k equal to p, then if I can show that it holds for k equal to p plus 1, then I am all set, right. I have proved it by induction, because I have shown that it holds for 1, right. And if I also show that if it holds for k equal to p, it automatically holds for k equal to p plus 1, then I have shown that it holds for all k, right. So, if it holds for k, let us suppose that it holds for k equal to p, then for k equal to p plus 1, we have delta p plus 1 yn is nothing but delta p delta yn. So, I move out one of the operators out, right. So, delta p delta yn, that is equal to delta p yn plus 1 minus yn, delta yn is equal to yn plus 1 minus ym, and from my expression here, for k equal to p, I get that expression delta p yn plus 1 is equal to yn plus 1 plus p minus p c1, and so on and so forth, right. And delta p yn So, delta p y n plus 1 was that, delta p y n is just if I replace n plus 1 by n, right, I get this, right, I get this, and then I subtract this from that. If I subtract this from that, what do I have on the left hand side? I have del p y n plus 1 minus del p y n, which is exactly this, right, del p y n plus 1 minus del p y n, and that I know is equal to del p plus 1 y n. So, the left hand side becomes del p plus 1 y m. On the right hand side, this term remains y n plus 1 plus p, and then if I look at coefficients of y n plus p, what do I have? I have a minus p c 1 and then I have a 1, right. This 1 I can represent as p c 0, because p c 0 is nothing but factorial p by factorial p, right. So, that is 1. So, that I can represent as p c 0. Then if I look at the coefficients of y plus n, y n plus p minus 1, what do I have? I have p c 2 minus, I might have made a mistake here, or I might have made a mistake here. So, that term is that term. So, that involves p c 2 and p c 1, that term involves p c 2 and p c 1, the next term is going to involve p c 3 and p c 2, and so on and so forth, right. And now this p c 1 plus p c 0 or this p c 2 plus p c 1 I can combine together. Why? Because in general p c nu plus p c nu minus 1 is equal to p plus 1 c nu, right, that is always true, right. So, this involves p c nu plus p c nu minus 1, terms like that. So, I can represent that as p plus 1 c mu, and hence I can write del p plus 1 y n is equal to y n plus 1 I have missed some terms here, y n plus 1 plus p, right, minus p plus 1 c 1 y n plus p, and so on and so forth, which is exactly as predicted by the formula, right. So, we have seen that we can write the kth difference operator in terms of this binomial, this expansion involving these binomial coefficients, right, and each depending on the order of the difference operator, we get more and more terms in those expressions, right. So, next time we are going to continue with this, and then we are going to try to establish relationships between these difference operators, between these various orders of difference operators and various orders of derivatives, right. So, if I have dn dxn, I want to be able to, if I have the nth derivative of a function with respect to a variable x, I want to relate that to my difference operator operating n times on that same function. And then I want to find out that what is going to be the difference between those two, between the derivative applied n times and the difference operator applied n times. What will be the difference? If I, instead of using the derivative, I use the difference operator, what will be the error, right? And how what is going to be specifically, what is going to be the leading term in that error, right? And that will allow us to write our differential equations, our partial differential equations in terms of differences, right, in terms of differences, while at the same time being fully aware of what are the errors that we are introducing when we introduce those differences in terms of, instead of the derivatives, right. Okay, thank you.